Then there was like one more different scheme, and in this scheme the same numbers like 0, 0, 0. Okay, in the second scheme, again, they did the same thing. They had the MSB for the sign. And for the positive numbers, again, it worked similarly. So if it is like, if it is a positive number, then this becomes like plus 0, plus 1, plus 2, and plus 3. But for the negative numbers, the way they came up with is like instead of having similarly, like again, this mentions a sign, okay, negative sign for 1. And now this number is not, if it is a negative number, then the way you evaluate is you take a complement of this number, like a, so 0, 0, okay. And this is a sign that we associate with complement in bits. And if you take a complement of 0, 0, this becomes 1, 1, okay. And now this is nothing but in binary, this is the value. This is in binary, okay. It's in binary, and in decimal, this is the value of 3. And so this number is nothing but minus 3. So the way you do that, we can do this for this particular thing. First, I see this most significant bit. I associate a minus with that. And for 0, 1, the value is not 1 directly, but instead the complement of this bit pattern. And the complement of this bit pattern is nothing but just flip those bits and find the value. By flipping those bits, by flipping the bits 0, 1, if you want to find the complement of 0, 1, in binary it's nothing but 1, 0. And this is nothing but 2. And I take this as the value of this number. And this is minus 1. And this again, try finding this out. This is going to be, when you flip this, it's going to be minus 0. Right? For the bit pattern 1, 1, 1, we get like, again, we have the issue of 2 bit patterns with the same for plus 0 and minus 0. And again, one more issue with this particular thing is like, based on what type of number is this, the processing needs to be handled differently for finding out the value of that particular number, which is a huge problem with computers. For while we are writing processes, then it's going to be like, okay, if this is a positive number, then you should do this. If this is a negative number, then we should like compute the value of this number in this way, okay? So this doesn't work again. But computers, like initially, computers were using these bit patterns, and they were using like sophisticated mechanisms to handle these things. And this particular thing is called ones complement. This is also one way of representing negative numbers, okay? And the way that is actually used, okay, in the modern systems is called 2's complement. And this is pretty interesting. So here, again, take the same 3, we are assuming just we have 3 bits, this. So with these things, again, it's the idea of having the most significant, but it's the same. So here the positive numbers are just going to be the same. It's going to be plus 0, plus 1, plus 2, and plus 3. But with the negative numbers, the way we are going to evaluate it is we are going to take something called the 2's complement. So let's first take the 0, 0. 2's complement of binary number 0, 0 is nothing but the way we usually compute 2's complement is like take the 1's complement of that and then add 1 to it. And so the 1's complement of 0, 0 is nothing but flipping the bits. And when you just add 1 to it, what happens? So with 1, 1, you're adding 1. So this becomes 1 plus 1 goes 0, carries over 1 here. That is another doing something wrong. Just a minute. So 1 plus 1, again 0, yeah, carry over 1 here. So if I add like 1, 1 in binary, if I add 1, 1 with the number 1 again in binary, it gives me 1 plus 1 gives like, it's basically 2. And the way we represent 2 is like having the 0 here and add the carry to the next level. So the 1 goes to the top at this point. And now when we're trying to add this 1 and 1, we get 0. And again, the carry is placed here. And this number is nothing but 4, right? And this is the value that we assign here. So this is going to be minus 4. And you can do it similarly for the other things. And it's just going to be minus 3, minus 2, and minus 1. Find the 2's complement. Of these 2 bits separately, this is going to be the value. This turns out to be an excellent way of encoding negative numbers, mainly because the issue of, if you can see here, the issue of 0 goes away. Just by adding this 1 in this, by calculating the 2's complement in a particular way, we are getting rid of that particular issue where 2 binary patterns represent the same number 0. Here in this, we just have 1 0, and so we really don't treat it as plus or minus 0, we just treat it as 0. Okay, and again, we have numbers from minus 1 to minus 4 and plus 1 to plus 3. And this is the reason why there was like 1 number more on the negative side, because we have used the bit pattern 0, 0, 0 with the most significant bit of 0, which is usually used for positive numbers, for representing 0. That's why we just got 1 number less on the positive side. And in negative side, we have like till minus 4. Does this make sense? Given a 2's complement number, and this is how signed numbers are represented in modern systems. Signed numbers use 2's complement arithmetic. And now before proceeding, let's first just see, if given a 4-digit number like 1001, okay, how can we figure out, if this is a binary number, how can we figure out what is the value of this particular number, okay, in 2's complement? One easier way than doing all these things is very similar to, we know that this position is 2 to the power of 0, 2 to the power of 1, 2 square, and 2 cube, right? So the easiest way is like for the first position, which we know is a negative number or a signed position, just instead of multiplying 1 with 2 to the power of 3, just multiply minus 1 with 2 to the power of 3. Because the signed bit is 1 here. And then you just add 0 times 2 square plus 0 times 2 power 1 plus 1 times 2 to the power 0. This turns out to be minus 8 plus 1, which is nothing but minus 7. So in 4 bits, minus 7 is represented like this. Make sense? And you can do this for any number, basically. And so what do you think is the bit pattern, like 1111 in binary? Like, can you tell this without even like calculating anything? Pardon? Negative 16. So with 4 bits, okay, with 4 bits, first let's think about this. Can negative 16 be an answer for this, okay? With 4 bits, the maximum that we can represent, even on the positive side, is just 15, right? Is that right? With 4 bits, the maximum we can represent is 15. So this is definitely not possible. This number is definitely not possible. So then let's figure out like how can we find this out? The one easier way to do things like this is like we know that this is going to be minus, let's say, 2 to the power of 3, right? And all these things, as we just saw previously, are going to be 2 to the power of 3 minus 1. Or in other words, if you add This is nothing but -8. And if you add, and these things are nothing but 4, 2, and 1. If you add all these things, it's going to be 7, and this is going to be -8. This is 2 to the power of 3 minus 2 to the power of 3. This is nothing but 2 to the power of 3 minus 1. And usually when you see a bit pattern of all ones, let's assume in this 4-bit number, if you see a bit pattern of all ones, then it's going to be -1. Then this bit pattern is going to represent -1. The same thing, think about that, the same thing will also apply to a 32-bit number. If you have a 32-bit number and if all the bits in the number is like 1, then if you interpret that number, the important thing is like how do we interpret that particular number? If we interpret that number using 2's complement form or using the signed as a signed number, all signed numbers are interpreted using the 2's complement version or encoding. If you're interpreting it using a 2's complement encoding, this number is going to become -1. But if you interpret the same number, this 4 digits, as an unsigned number, okay, what is the value of this? It's just going to be 15. It is just going to be the same bit pattern as an unsigned number is just going to be 15. And this particular thing creates a lot of issues in C programming. We are going to see like what are those issues, okay? Any questions about this? Feel free to like ask any questions if you have, because if what do we mean by 2's complement, if this is not clear, then the problems associated with that will not be very clear. Okay, let's write some like small code snippets to understand like what we are doing here. Okay, let's have a number like int. So when I just say int, it's going to be a signed number. Okay, it's going to be a signed number. Let's have this number to be, let's assume -1. Okay, and let's try printing this number. I'm initially just printing it as a decimal, so it really, there is nothing fancy happening here. So if we I did not add return 0. Just prints -1 as it is in decimal. It just interprets this number as -1. What happens if we print it in hexadecimal form? Any ideas what is going to be the answer now? So remember, like this number is going to, internally it's just a bit pattern, and this bit pattern is going to be encoded using the 2's complement arithmetic or 2's complement encoding that we just saw. And so -1, as we saw, like even how many bits, like here we have like 32 bits. And if we have 32 bits and if all those bits are 1, then that is that bit pattern for -1. And so this number is just going to be some sequence of F's. And we can see here that 1, 2, 3, 4, 5, 6, 7, 8. There are 8 F's here, and each hexadecimal F is just the number 15 in hexadecimal or 4 bits of ones. And each of this bit takes, like each hexadecimal digit takes 4 bits. So we have 4 times 8, 32 bits, 32 things that says that's 1. Make sense? So now you can try like maybe changing that number to a positive number. Let's assume it's just like 100 or something simpler like 15, okay? And I'm trying to print the same number using decimal and hexadecimal. So as you can see here, 15 is being printed in decimal, and when you are printing in hexadecimal, it is not printing the leading zeros. Okay, it is just printing the value, some value that has some bit pattern. So even though the number has 32 bits within it, only the 4 bits are being printed, which are actually getting some values. The trailing zeros are omitted.